Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. 252 million years ago, Earth experienced its darkest hour. The planet's biosphere collapsed in what scientists call the Permian-Triassic Extinction event, though it carries a more ominous nickname, the Great Dying. This catastrophe dwarfs every other mass extinction in Earth's history, including the asteroid impact that eliminated the dinosaurs 66 million years ago. The numbers are staggering. Approximately 96% of marine species vanished forever. On land, 70% of terrestrial vertebrates disappeared. Even insects, typically resilient survivors of environmental upheaval, suffered their only known mass extinction. Entire ecosystems collapsed, leaving behind a planet so barren that it resembled an alien world more than the vibrant Earth we know today. To understand this catastrophe's magnitude, we must journey back to the late Permian period, roughly 255 million years ago. Earth looked dramatically different then. The supercontinent Pangaea dominated the globe, stretching from pole to pole like a massive landmass surrounded by the vast Pan-Thalassic Ocean. This continental configuration created extreme climate conditions, with scorching desert interiors and limited coastal areas where life could flourish. The late Permian world teemed with unique life forms. Synapsids, our distant mammalian ancestors, ruled terrestrial ecosystems. Massive predators like gorgonopsids stalked plant-eating pariasaurs across ancient landscapes. In the oceans, diverse marine communities thrived in shallow seas, including countless species of brachiopods, crinoids, and early reef-building organisms. Yet beneath this apparent prosperity, Earth systems were becoming increasingly unstable. Volcanic activity was intensifying across the planet, particularly in what is now Siberia. Ocean chemistry was shifting as atmospheric composition changed. Climate patterns were becoming more erratic, with temperature fluctuations that stressed ecosystems worldwide. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. The extinction event didn't happen overnight. Scientific evidence suggests the Great Dying unfolded over several thousand years, though some phases occurred much more rapidly. This timeline makes it particularly fascinating from a scientific perspective, as researchers can trace the gradual build-up of environmental stresses that ultimately triggered the collapse. What makes the Permian-Triassic extinction especially significant is its role as Earth's closest brush with complete sterilization. Some scientists estimate that life came within a whisker of total extinction. The event represents a natural experiment on a planetary scale, showing us how interconnected Earth systems truly are and how quickly they can unravel when pushed beyond critical thresholds. The recovery was equally remarkable. It took approximately 10 million years for biodiversity to fully recover, and when it did, Earth's biosphere had been fundamentally transformed. The Triassic period that followed saw the rise of dinosaurs, the first mammals, and modern marine ecosystems. In many ways, the Great Dying reset life's evolutionary trajectory, creating opportunities for new forms to emerge and dominate. Understanding this ancient catastrophe isn't merely an academic exercise. The Permian-Triassic extinction offers crucial insights into how planetary systems respond to rapid environmental change. By studying the mechanisms that drove Earth's biosphere to the brink of collapse, scientists can better understand the resilience and vulnerability of life itself. Knowledge that becomes increasingly relevant as we face our own era of rapid environmental transformation. Deep beneath Siberia lies evidence of one of the most catastrophic volcanic events in Earth's history. The Siberian Traps, a massive igneous province covering over 2 million square kilometers, represents the primary suspect in the Great Dying mystery. This wasn't ordinary volcanic activity. It was planetary-scale destruction that fundamentally altered Earth's atmosphere, oceans, and climate. Large igneous provinces form when enormous volumes of molten rock erupt from deep within Earth's mantle. The Siberian Traps eruption began approximately 252 million years ago. coinciding precisely with the onset of the Permian-Triassic extinction. This timing isn't coincidental. It's the smoking gun that connects volcanic catastrophe to biological collapse. To comprehend the scale involved, consider that the Siberian traps released an estimated 4 million cubic kilometers of lava and volcanic material. This volume could bury the entire continental United States under a layer nearly 400 meters thick. But the lava itself was only part of the story. The eruptions released massive quantities of gases into the atmosphere, fundamentally altering Earth's atmospheric composition. The volcanic activity occurred in multiple phases over several 100,000 years. Each phase brought new waves of environmental stress, preventing ecosystems from recovering between eruptions. Paleontologists have identified at least 3 major extinction pulses during this period, each corresponding to intensified volcanic activity. This stepwise pattern suggests that life was repeatedly knocked down just as it began to recover. Carbon dioxide emissions from the Siberian traps were unprecedented in Earth's history. Scientists estimate that these eruptions released between 30,000 and 100,000 gigatons of carbon dioxide into the atmosphere. To put this in perspective, current annual human carbon dioxide emissions total approximately 40 gigatons. The Siberian traps released the equivalent of hundreds to thousands of years of current human emissions in a geological instant. But carbon dioxide was only one component of the toxic cocktail. The eruptions also released enormous quantities of sulfur dioxide, which formed acid rain and volcanic smog. Hydrogen sulfide, a poisonous gas that smells like rotten eggs, poured into the atmosphere in concentrations that would have been lethal near the volcanic centers. Chlorine and fluorine compounds added to the atmospheric chaos, creating conditions hostile to most forms of life. The volcanic eruptions didn't just affect the atmosphere, they fundamentally altered the landscape itself. Much of the volcanic activity occurred through explosive eruptions that sent ash clouds circling the globe. These ash clouds blocked sunlight, causing temporary cooling periods that stressed plant communities worldwide. When the ash settled, it created massive deposits that buried entire ecosystems. Perhaps most devastatingly, many of the Siberian trap eruptions occurred through sedimentary rocks rich in organic matter and evaporite deposits. When molten lava intruded into these formations, it cooked organic carbon and released additional greenhouse gases. Salt deposits vaporized, releasing chlorine and other halogens that damaged the ozone layer and increased harmful ultraviolet radiation reaching Earth's surface. The eruptions also created massive underground intrusions called sills and dikes. These intrusions heated surrounding rock formations, triggering the release of even more gases. Some researchers estimate that contact metamorphism from these intrusions released as much carbon dioxide as the direct volcanic emissions themselves, effectively doubling the atmospheric impact. Recent research has revealed that the Siberian traps weren't just geographically isolated events. The volcanic activity may have triggered a cascade of environmental changes that affected the entire planet. Evidence suggests that volcanic loading stressed Earth's crust, potentially triggering increased seismic activity and additional volcanic eruptions in other regions. The Siberian traps represent nature's most extreme example of how geological processes can devastate planetary environments. Their legacy extends far beyond the Permian-Triassic boundary, fundamentally reshaping our understanding of how volcanic activity can drive mass extinction events and planetary environmental change. As volcanic gases poured into Earth's atmosphere, the planet transformed into a greenhouse hell that would have been unrecognizable to modern eyes. The atmospheric chemistry changes triggered by the Siberian traps created a cascade of environmental disasters that made survival nearly impossible for most life forms. Carbon dioxide concentrations skyrocketed to levels unprecedented in Earth's history. Before the eruptions, atmospheric carbon dioxide levels were already elevated compared to today, measuring approximately 1,000 parts per million. The volcanic emissions drove concentrations to over 8,000 parts per million, more than 20 times current levels. This massive greenhouse gas injection triggered runaway global warming that persisted for hundreds of thousands of years, global temperatures soared by 8 to 16 degrees Celsius above pre-extinction levels. In equatorial regions, surface, temperatures may have reached 50 to 60 degrees Celsius, making vast areas of the planet uninhabitable for complex life. Ocean surface temperatures in tropical regions approached 40 degrees Celsius, creating thermal barriers that prevented normal ocean circulation patterns. The extreme warming created positive feedback loops that amplified the crisis. As temperatures rose, permafrost melted, releasing additional methane and carbon dioxide from frozen organic matter. Warmer oceans released dissolved carbon dioxide, further increasing atmospheric concentrations. Reduced ice cover decreased Earth's albedo, causing the planet to absorb more solar radiation and warm even further. Acid rain became a global phenomenon as sulfur dioxide from volcanic eruptions combined with atmospheric water vapor to form sulfuric acid. Rain acidity levels dropped to values comparable to modern battery acid, with pH values as low as 2 to 3. This acidic precipitation dissolved carbonate rocks, killed vegetation, and poisoned freshwater systems across the planet. Soil chemistry changed dramatically, making it difficult for plants to extract essential nutrients. The atmospheric sulfur compounds created another devastating effect: global dimming. Sulfur dioxide formed aerosol particles that reflected sunlight back to space, creating a cooling effect that temporarily counteracted greenhouse warming. However, this dimming reduced photosynthesis efficiency, causing widespread plant die-offs. The combination of heat stress and reduced light availability created a double blow to primary productivity. Ozone depletion added another layer of atmospheric catastrophe. Chlorine and bromine compounds released by volcanic activity destroyed stratospheric ozone, allowing harmful ultraviolet radiation to reach Earth's surface at lethal intensities. This increased UV radiation caused widespread mutations, cancer, and death in organisms that had evolved under the protection of a healthy ozone layer. Hydrogen sulfide concentrations reached toxic levels in many regions. This poisonous gas, produced by volcanic emissions and enhanced by bacterial activity, in oxygen-depleted environments, created dead zones where complex life couldn't survive. Hydrogen sulfide concentrations may have reached several hundred parts per million in some areas, levels that would cause rapid death in most animals. The atmospheric chaos disrupted weather patterns worldwide. The extreme temperature gradients between different regions created massive storm systems and unprecedented weather variability. Monsoon patterns collapsed, turning fertile regions into deserts. Atmospheric circulation patterns shifted dramatically, redistributing heat and moisture in ways that stressed ecosystems adapted to stable climate conditions. Methane emissions added to the greenhouse gas cocktail. Volcanic activity released methane directly, while changing environmental conditions triggered additional methane release from natural sources. Wetland environments, stressed by temperature and acid rain, began producing more methane through anaerobic decomposition. Ocean warming released methane from seafloor sediments, creating methane hydrate destabilization events. The atmospheric changes created a planet-wide chemical warfare scenario. Multiple toxic gases combined to create an atmosphere that was simultaneously too hot, too acidic, too toxic, and too UV intense for most life forms. The few organisms that survived had to adapt rapidly to conditions unlike anything in Earth's previous history. These atmospheric changes persisted long after the volcanic eruptions ended. Carbon dioxide remained elevated for millions of years, maintaining greenhouse conditions that prevented normal ecosystem recovery. The planet's climate system had been pushed into a new stable state, one that was fundamentally hostile to the life forms that had previously dominated Earth's biosphere. While the atmosphere burned with toxic gases, Earth's oceans underwent their own catastrophic transformation. The marine realm, which had harbored the planet's richest biodiversity for hundreds of millions of years, became a realm of death as ocean chemistry shifted beyond the tolerance limits of most marine life. Ocean acidification struck with unprecedented severity. As atmospheric carbon dioxide concentrations soared, the oceans absorbed massive quantities of this gas, forming carbonic acid that drove seawater pH down by approximately 0.7 units. This may seem small, but pH is measured on a logarithmic scale, meaning ocean acidity increased by roughly 500%. Marine organisms that had evolved elaborate calcium carbonate shells and skeletons found themselves literally dissolving in increasingly corrosive seawater. The effects on shell-building organisms were catastrophic. Brachiopods, which had dominated marine ecosystems for 300 million years, suffered near-complete extinction. Corals, bryozoans, and countless other calcifying organisms watched their protective structures weaken and dissolve. Even microscopic plankton with calcium carbonate shells faced extinction, disrupting the entire marine food web from its foundation. Simultaneously, the oceans were becoming starved of oxygen in a process called oceanic anoxia. Rising temperatures reduced oxygen solubility in seawater, while increased organic matter decomposition consumed available oxygen faster than it could be replenished. Vast regions of the ocean became anoxic zones, where complex marine life simply couldn't survive. The anoxic conditions triggered a shift in marine bacterial communities. Anaerobic bacteria began producing hydrogen sulfide through sulfate reduction, turning large portions of the ocean into toxic, purple-colored waters. Hydrogen sulfide concentrations reached levels that were directly poisonous to marine animals, creating underwater dead zones that expanded across entire ocean basins. Evidence for oceanic hydrogen sulfide poisoning comes from distinctive purple and green sulfur bacteria fossils found in Permian-Triassic boundary rocks worldwide. These bacteria only thrive in hydrogen sulfide-rich, oxygen-free environments. Their presence in formerly diverse marine sediments tells the story of oceans transformed from oxygen-rich havens into toxic, bacterial-dominated wastelands. Temperature. Stratification in the oceans broke down normal circulation patterns. Typically, cold polar waters sink and flow toward the equator, carrying oxygen to deep ocean environments. But extreme global warming reduced temperature differences between polar and equatorial regions, weakening thermohaline circulation. This reduced the ocean's ability to distribute oxygen and nutrients, creating stagnant conditions that favored bacterial growth over complex marine life. Marine food webs collapsed from both top and bottom. Primary productivity plummeted as toxic conditions killed phytoplankton communities. Without these microscopic plants, the entire marine food chain lost its foundation. Simultaneously, large marine predators faced direct poisoning from hydrogen, sulfide and acid conditions, creating a complete ecosystem breakdown. Carbonate platform collapse marked another devastating marine impact. Shallow water carbonate environments, which today support coral reefs and diverse marine communities, completely disappeared during the extinction. These platforms had been major sites of biological diversity and carbonate rock formation. Their destruction eliminated crucial nursery habitats for countless marine species. The few marine organisms that survived the initial catastrophe faced ongoing challenges. Reduced genetic diversity made populations vulnerable to additional environmental stresses. Many survivor species were ecological generalists that could tolerate extreme conditions, but couldn't rebuild the complex ecosystem relationships that had previously characterized marine environments. Recovery patterns in marine environments reveal the severity of the crisis. Unlike terrestrial ecosystems, which began showing signs of recovery within a few million years, marine environments remained depauperate for nearly 10 million years. New marine ecosystems that eventually emerged were fundamentally different from their Permian predecessors, with different dominant groups and simplified food web structures. Recent research has identified additional marine impacts, including trace metal poisoning from volcanic emissions and disrupted nutrient cycling, that persisted long after the initial extinction event. The oceans had become not just inhospitable, but actively hostile to the life forms that had previously called them home, representing Earth's most severe marine crisis in the planet's entire history. On land, the Great Dying manifested as a complete breakdown of terrestrial ecosystems that had taken millions of years to develop. The combination of extreme heat, acid rain, and toxic atmospheric conditions created a planetary wasteland where Even the most adaptable life forms struggled to survive. Plant communities faced a multi-pronged assault that began with direct atmospheric toxicity. Sulfur dioxide concentrations reached levels that were directly poisonous to plant tissues, causing widespread leaf damage and killing entire forests. Acid rain with pH levels below 3 dissolved protective waxy coatings on leaves and leached essential nutrients from soils, making it impossible for plants to maintain normal metabolic functions. The extreme greenhouse warming pushed terrestrial temperatures beyond the physiological limits of most plant species. In equatorial regions, daytime temperatures regularly exceeded 50 degrees Celsius, while nighttime temperatures remained above 30 degrees Celsius. These conditions triggered widespread plant mortality, as even drought-adapted species couldn't survive the sustained thermal stress. Photosynthesis efficiency plummeted due to multiple environmental stresses. High temperatures reduced the efficiency of crucial enzymes involved in carbon fixation. Simultaneously, volcanic aerosols and atmospheric haze reduced available sunlight by up to 30%, creating a paradoxical situation where plants faced both extreme heat and insufficient light for normal growth. Soil ecosystems collapsed as acid rain altered fundamental soil chemistry. Essential nutrients like calcium and magnesium were leached away, while toxic metals like aluminum became more bioavailable in acidic conditions. Soil organisms, from bacteria to invertebrates, faced mass mortality, disrupting nutrient cycling processes that had sustained terrestrial ecosystems for hundreds of millions of years. The breakdown of plant communities had cascading effects throughout terrestrial food webs. Herbivorous animals faced starvation as their food sources disappeared. Large herbivores like pariasaurs and dicynodonts, which had dominated late Permian landscapes, suffered massive population crashes. Their extinction eliminated a crucial link between primary producers and higher-level consumers. Carnivorous animals faced a double crisis. Not only were their prey species disappearing, but many predators also suffered direct poisoning from toxic atmospheric conditions. Large predators like gorgonopsids required substantial territories and regular food sources to survive. As ecosystem productivity collapsed, these apex predators were among the first to face extinction. Terrestrial arthropods experienced their only known mass extinction during this event. Insects, typically among the most resilient organisms during environmental crises, suffered unprecedented mortality rates. Many insect groups that had diversified during the Carboniferous and Permian periods vanished entirely, eliminating crucial pollinators and decomposers from terrestrial ecosystems. Forest ecosystems transformed into barren landscapes resembling modern deserts. Paleobotanical evidence shows that diverse late Permian forests were replaced by simple, low-diversity plant communities dominated by stress-tolerant species. In many regions, complex forest ecosystems were replaced by nearly barren landscapes, with only scattered hardy shrubs and ferns. Freshwater ecosystems on land faced their own crisis as acid rain poisoned rivers and lakes. Aquatic plants died off, followed by freshwater fish and amphibian populations. Many freshwater environments became too acidic to support complex life, creating terrestrial dead zones that persisted for thousands of years. The few terrestrial survivors were typically small generalist species that could tolerate extreme environmental conditions and had flexible dietary requirements. Many were burrowing animals that could escape surface heat and toxic conditions by living underground. These survivors became the ancestors of Triassic fauna, but their limited diversity meant that terrestrial ecosystem recovery was extremely slow. Seed dispersal mechanisms broke down as both plants and their animal dispersers faced extinction. This disrupted plant reproduction and colonization of new areas, slowing ecosystem recovery even further. Many plant species that had relied on specific animal partnerships for reproduction never recovered from the extinction event. The terrestrial fossil record shows that ecosystem recovery took approximately 5 to 10 million years, much longer than recovery from other mass extinctions. When new ecosystems finally emerged, they were fundamentally different from their Permian predecessors. dominated by new groups of plants and animals that had evolved to thrive in post-apocalyptic conditions. In the aftermath of Earth's greatest catastrophe, life demonstrated its remarkable resilience through the survival of small, highly adaptable organisms that would eventually repopulate the planet. These survivors employed diverse strategies to endure conditions that had eliminated 96% of marine species and 70% of terrestrial vertebrates. Small body size emerged as one of the most important survival traits. Tiny organisms required fewer resources and could exploit microhabitats that provided protection from extreme environmental conditions. Many surviving vertebrates were small cynodonts, early relatives of mammals that weighed less than a few kilograms. Their modest energy requirements allowed them to persist on limited food resources when ecosystem productivity collapsed. Burrowing behavior provided crucial protection from surface environmental extremes. Many surviving vertebrates, including various therapsid groups, were fossorial species that spent significant time underground. Burrows offered protection from extreme surface temperatures, toxic atmospheric gases, and harmful ultraviolet radiation. Underground environments also maintained more stable temperature and humidity conditions. Generalist feeding strategies proved essential for survival. Organisms with specialized diets faced extinction when their preferred food sources disappeared, but generalists could switch between different food sources as availability changed. Many surviving mammals and reptiles were omnivores that could consume both plant and animal matter, allowing them to adapt to rapidly changing food availability. Rapid reproductive rates helped some species maintain viable populations despite high mortality rates. Small mammals and reptiles that could reproduce quickly and produce large numbers of offspring had better chances of survival than slow-reproducing megafauna. High reproductive output allowed populations to recover rapidly when environmental conditions temporarily improved. In marine environments, disaster taxa, organisms that thrive in disturbed conditions, began to dominate ecosystems. Small gastropods and bivalves with simple shell structures survived the ocean acidification that eliminated more complex calcifying organisms. These simple mollusks could rapidly colonize disturbed seafloor habitats and rebuild basic marine food. Webb's microbial communities showed remarkable adaptability during the crisis. Many bacteria and archaea could switch between different metabolic pathways depending on environmental conditions. Some groups thrived in the anoxic, hydrogen sulfide-rich conditions that killed most complex life. These microorganisms maintained basic ecosystem functions, like nutrient cycling during the worst phases of the extinction. Plant survivors were typically stress-tolerant species with efficient water use and robust physiological systems. Seed ferns and early conifers possessed adaptations for surviving in harsh, dry conditions. Many surviving plant groups had waxy cuticles that provided protection against acid rain and efficient root systems for extracting nutrients from degraded soils. Early recovery showed interesting patterns of ecological opportunism. The first post-extinction communities were often dominated by single species that could exploit vacant ecological niches. These disaster assemblages had low diversity but high abundance, representing the first steps toward ecosystem rebuilding. Lystrosaurus, a pig-sized herbivore, became so dominant in early Triassic terrestrial ecosystems that some fossil sites contain almost nothing else. Evolutionary innovation accelerated among survivor lineages. The environmental pressures of the extinction event drove rapid evolutionary changes that led to new adaptations. Early archosaurs, the group that would eventually include dinosaurs and crocodiles, began diversifying rapidly in the Triassic period, taking advantage of vacant ecological niches left by extinct Permian groups. Marine recovery showed signs of evolutionary experimentation. New types of shell structures evolved among surviving mollusks, some of which were more resistant to acidic conditions. Early scleractinian corals began developing new skeletal architectures that would eventually lead to modern reef ecosystems, though full reef recovery took millions of years. Geographic refugia played crucial roles in survival patterns. Some regions, particularly at higher latitudes or in areas with unusual geological conditions, provided more favorable environments where extinction rates were lower. These refugia served as sources for recolonization when global conditions began to improve. The extinction event created evolutionary bottlenecks that had lasting effects on Earth's biosphere. Many major groups that survived did so with severely reduced genetic diversity, influencing their subsequent evolutionary trajectories. However, these survivors proved that life's creativity and adaptability could overcome even the most severe planetary crises, setting the stage for the remarkable recovery that would follow. The recovery from Earth's greatest catastrophe unfolded over millions of years, revealing important patterns about how life rebuilds after planetary-scale disasters. This recovery process offers crucial insights into both the resilience of life and the long-term consequences of extreme environmental change. Early Triassic recovery began slowly, with disaster taxa dominating simplified ecosystems for the first 1 to 2 million years after the extinction. These early communities had extremely low diversity, but relatively high biomass, representing life's first tentative steps back from the brink of total extinction. Lystrosaurus populations exploded across Pangaea, creating some of the most monotonous fossil assemblages in Earth's history. Marine recovery followed a predictable sequence that scientists call the Lazarus effect. Many groups that appeared to go extinct during the crisis actually survived in small refugial populations before expanding again when conditions improved. However, full marine ecosystem recovery took approximately 10 million years, much longer than recovery from other mass extinctions. The Middle Triassic marked a turning point in recovery patterns. New evolutionary radiations began filling ecological niches left vacant by Permian extinctions. Archosaurs diversified rapidly, giving rise to the first dinosaurs, pterosaurs, and modern crocodile groups. Marine reptiles like ichthyosaurs and plesiosaurs evolved to fill niches previously occupied by extinct Permian marine predators. Reef ecosystems showed particularly slow recovery. Permian reefs built by complex communities of bryozoans, brachiopods, and rugose corals were replaced much later by entirely different reef-building organisms. Modern scleractinian corals didn't become major reef builders until the Middle Triassic, and full reef ecosystem complexity wasn't restored until the Jurassic period, over 50 million years later. The extinction fundamentally reset evolutionary trajectories. Many dominant Permian groups never recovered their former diversity, while previously minor groups underwent massive adaptive radiations. Mammals evolved from small cynodont survivors, eventually becoming one of Earth's most successful vertebrate groups. Dinosaurs rose from humble archosaur ancestors to dominate terrestrial ecosystems for over 150 million years. Modern climate change research has drawn important parallels with the Permian-Triassic extinction. The volcanic carbon dioxide emissions that drove the ancient crisis released greenhouse gases at rates comparable to current human emissions, though over much longer timescales. Ocean acidification patterns from the ancient event provide crucial insights into how marine ecosystems respond to rapid atmospheric carbon dioxide increases. Scientists study the Great Dying, using multiple approaches that reveal different aspects of the catastrophe. Geochemical analysis of boundary rocks provides information about atmospheric and ocean chemistry changes. Carbon isotope ratios reveal disruptions to the global carbon cycle, while sulfur isotopes indicate volcanic emissions and ocean anoxia patterns. High-precision uranium-lead dating of zircon crystals from volcanic ash layers has revealed the precise timing relationships between volcanic eruptions and extinction pulses. These techniques show that the extinction occurred over several 100,000 years, with multiple phases of crisis and partial recovery. Paleomagnetic studies of rock formations help reconstruct ancient climate patterns and the geographic distribution of environmental changes. These analyses reveal that some regions experienced more severe conditions than others, explaining patterns of survival and extinction in different parts of the world. The Permian-Triassic extinction serves as a natural laboratory for understanding planetary system behavior under extreme stress. It demonstrates how interconnected Earth systems truly are, and how changes in one system can cascade through others to create global catastrophe. The event shows that even life's remarkable adaptability has limits when environmental change exceeds critical thresholds. Perhaps most importantly, the Great Dying reveals that recovery from severe environmental crises is possible but slow. Life's creativity and resilience ultimately prevailed, but full ecosystem recovery required millions of years and produced a fundamentally different biosphere. The survivors didn't simply restore previous ecosystems, they created entirely new ones adapted to post-catastrophe conditions. Understanding Earth's greatest extinction provides perspective on both the fragility and resilience of planetary life support systems. It reminds us that while life has survived every crisis in Earth's history, the cost of planetary-scale environmental change is measured not in years or decades, but in millions of years of impoverished ecosystems and lost evolutionary potential. The Great Dying stands as both a testament to life's ultimate resilience and a warning about the true timescales of recovery from planetary environmental catastrophe.